Oh, I need to accept. Okay.
Yes, you might.
Okay, can I start?
Yeah, please start, yeah.
Yeah, okay. So let me begin by thanking the organizers for the opportunity to speak here. Today, I will tell you about logarithmic corrections to black hole entropy from weak Jacobi forms, where these weak Jacobi forms will have some features we're familiar with from holography. And this is based on a paper that appeared a few months ago, together with Susan Bintania, Alejandra Castro, and Diego Lisca. So let me begin by giving some motivation, and the motivation comes from ADS-CFT. So in ADS-CFT, we know that a semi-classical description of quantum gravity, say in ADS-3, imposes several holographic conditions on the dual CFT2. So one of these conditions that is very well known is the existence of a large n limit. So here, n is identified with the central charge of the CFT, which is inversely proportional to Newton's constant. So when Newton's constant is small, the central charge and n are large. In addition to this, we have other properties like large n factorization, which tells us that correlation functions of an n number of operators should scale in the large n limit, as shown here. And in addition to this, we also require a spectrum to be sparse, which means that the spectrum of light states doesn't grow with n. So both of these properties are properties that we require from the light states in our theory. And in this talk, I will be paying special attention to this condition of sparseness in the context of weak Jacobi forms. So before I jump to weak Jacobi forms, let me mention this work by Hartman, Keller, and Stoika, who made the sparseness condition very precise. So by sparseness, they meant that the density of light states in the theory, so here the light states are states that lie below the black hole threshold. So here E is less than 0, 0 is the black hole threshold, minus C over 12 is the energy of the vacuum. So they required the density of states, the density of these states to grow not larger than this Hagedorn type of growth, so an exponential that scales linearly with the energy. And with this assumption on the light states, they were able to show that if you use this condition of sparseness plus moderate invariance of the CFT plus the large n limit, that the universal, that the free energy of this theory, of this CFT2, would be universal. So here the free energy is defined as the log of the CFT partition function. This is the torus partition function. Beta is the inverse temperature. And this is defined in the usual way. Here, rho is the density of states. E is the energy of the state. And by having a universal free energy, I mean that they found that the log of the partition function in this large n limit with these conditions equals the log of the partition function of 3D gravity, computed in the semi-classical approximation. In particular, this means that if you compute the log of the partition function of the CFT, you find these two types of behavior. So when the inverse temperature is greater than 2 pi, so this is at low temperatures, the log of the partition function is dominated by this expression, which comes from the vacuum, whereas when you're at high temperatures or small values of beta, the inverse temperature, then it's dominated by its modular image under a modular S transformation. Okay, and then it matches the answer that you get from a BTC black hole in the bulk side of the ADS-3 CFT2 correspondence. This result up here is defined in the, or is obtained in the canonical ensemble. You can translate this to the microcanonical ensemble, and you find that there's a universal density of states. So in this plot, from the CFT point of view, I plotted the energy. The vacuum has in these conventions energy minus C over 12. By assumption, HKS, Hartman, Keller, Stoika, assume that the density of light states satisfies this condition. So this is what we have on this region. Then by exploiting this fact that the partition function in this large n limit with these conditions is universal, then you find that the density of high energy states is given by the Cardy formula, okay? So here we've distinguished again between light states and heavy states. From the gravitational point of view, these light states correspond to perturbative states in gravity, whereas the heavy states correspond to black holes. And we know that this Cardy formula indeed reproduces the entropy of black holes, okay? So what's interesting about this HKS analysis is that it shows that the result is not sensitive to the light spectrum of the CFT. So the result that they found turns out to be universal for any holographic CFT, meeting the conditions that we mentioned before. In addition to this, it extends the regime of validity of Cardy's formula. So Cardy's formula was originally derived in a regime where the energy of the state, whose density you're trying to estimate, it's much greater than C. But once you impose this sparseness condition using HKS, you find that now you can describe the density of states whose energy are of the order the central charge. And of course, you assume the central charge is much greater than 1 because you're still interested in having a semi-classical bulk description. And so using this HKS approach with this precise form of the sparseness condition actually justifies the derivation of the Bekenstein-Hawking entropy for BTC black holes in the semi-classical regime where you assume that C is much greater than 1, but you want to describe black holes of order whose energies are of order C, not necessarily much larger than C. Okay, so why am I mentioning this story about HKS and holography in an ADS3-CFT2 is because many black holes in supergravity feature an ADS3 near horizon geometry or an ADS2 near horizon geometry that can be uplifted to ADS3. This is something I'll discuss later on. And so the question that I would like to ask in this talk is, what do the holographic conditions that impose on a CFT2, like a large central charge and sparseness, have to say of the entropy of such BPS black holes that have a near horizon ADS3 region? So to summarize what I will tell you about today, what I will do is I will extract the asymptotic density of states of what I will call holographic weak Jacobi forms. So these would be Jacobi forms for which I can interpret as a gravitational path integral. So that's what I mean by holographic. And I will focus on the logarithmic corrections to Cardy's formula, and I will show the following. So the log of the density of states is going to be given by an expression that is Cardy's formula here. And there's going to be logarithmic corrections. And the goal is to determine these two coefficients, AE and AC. And it turns out that the answer depends on the sparseness condition I impose on the light states. So very soon I'm going to distinguish between two kinds of densities for these light states, fast versus slow, that I will define shortly. And then we'll find that there's a universal regime in which these coefficients here that determine the log corrections to the entropy are independent of the details of the light states, okay? They do not depend on whether the light states grow fast or grow slow. These answers are universal, and this will allow us to extend the validity of Cardy's formula for these weak Jacobi forms beyond what HKS originally considered. Of course, they consider a full partition function of a CFT, but still, this is something that we will do in the context of weak Jacobi forms. And we will show that indeed the log corrections of a certain kind of black holes, so quarter BPS black holes in 4D n equals 4 supergravity, turn out to fall within the regime, this universal regime of a weak Jacobi form, okay? But in addition to this, we will also find that there's a non-universal regime, in which case these coefficients, or what we mean by this non-universal regime, is that these coefficients are sensitive to the density of light states. So they depend on the details of the theory on how the spectrum of light states grows. And it turns out that there are examples where this is realized. So the logarithmic corrections of BNPV black holes and black holes and half BPS black holes in 4D supergravity and n equals 2 supergravity turn out to be captured by weak Jacobi forms in this non-universal regime, Okay, so that's basically what I will try to show today. And so the plan of the talk is as follows. I've given you some motivation of why I'm interested in seeing the repercussions of sparseness on weak Jacobi forms. Then now what I will do now is I will tell you a little bit about weak Jacobi forms. Then I will tell you how I extract the asymptotics of these weak Jacobi forms. And finally, I will try to apply these formulas to extract the corrections, the log corrections to black hole entropy. Okay. So let me begin with talking about weak Jacobi forms. So this will be like a very quick review of some of their properties, just to make sure we are all on the same page. So weak Jacobi forms are holomorphic functions of this form. They're characterized by a weight that I denote here by k, and then index t. And they have many interesting features. So in particular, they transform nicely under modular transformations. So they have a factor that depends on the weight and a factor that depends on this variable z, which we can think of as a chemical potential. In the context of the HK story that I mentioned at the beginning, these factors are not there. So the partition function, the torus partition function of a CFT2 is modular invariant. Instead, the weak Jacobi form, we can say, is modular covariant. So it transforms under modular transformations, but it transforms in this nice way. In addition, weak Jacobi forms transform under spectral flow transformations in this way, where you shift this chemical potential Z. In this way, you get this extra additional phase, and this transformation is important in determining some of the properties of these forms, as we will see soon. And they admit a Fourier expansion, which I've written down here, where these CNLs here are integers. These are the density of our states. And I have put this sum in blue because I haven't told you the relationship between n and L in this sum. So this expression is still not valid for a weak Jacobi form unless I tell you precisely under which the relationship between an n and L in this sum, okay? So, but I will tell you this now. So the first two conditions, namely modular transformations and the elliptic transformations of these weak Jacobi forms, imply that these Fourier coefficients, these CNLs, depend only on two variables that depend on the discriminant, which is this combination of variables, and on the value of L, this charge that appears here, modulo 2 times the index. Okay, and there are different types of forms, and this type of forms will determine the how to actually write this Fourier expansion. So you have like Jacobi forms where the discriminant is greater or equal than 0. You have these Jacobi cos forms that are written here. There are some other types of forms, but the ones we're interested in today are weak Jacobi forms. And these weak Jacobi forms are characterized by having a negative discriminant, but that cannot be arbitrarily negative. So there's a minimum value of the discriminant, which here I label by delta naught, and it's given by the index t of the weak Jacobi form in this way. So the spectrum of the weak Jacobi form has two types of states. There are states that have a negative discriminant. They're known as polar states. In the context of holography, which is where we want to use all of this technology, these correspond to light perturbative states in gravity. Here, delta naught, which is the lowest value of the discriminant, I will usually call this the most polar state. This is the state with the minimum value of delta naught. But in addition to these polar states that describe this negative region of the discriminant, there are non-polar states that have a positive discriminant. And in the context of gravity, these would correspond to heavy black hole states. Okay, so some additional reasons why one would be interested in studying weak Jacobi forms is that they're simpler than a partition function, for example, the partition function of a CFT, but they have a richer structure than a chiral partition function. In addition, the polar states of the weak Jacobi form completely determine the non-polar states. So once you know the CNL coefficients of the polar terms, then you can you have a formula to describe the coefficients of the non-polar ones. And as is well known, weak Jacobi forms are relevant in string theory, in the counting of black hole microstates, and in ADS-CFT. For example, the elliptic genus of a CFT with n equals 4 supersymmetry is a weak Jacobi form that has weight 0 and whose most polar state, so the discriminant of the ground state in the elliptic genus, is related to the central charge in this way. But we don't want to look at just generic weak Jacobi forms. We want to look at a special kind of weak Jacobi forms that we call holographic weak Jacobi forms. And so these are weak Jacobi forms that meet the following two conditions. First, the discriminant of the most polar state, rather the absolute value is much greater than 1. You see this is motivated by the example up here and many other examples that we have in ADS-CFT, where the minimum value of the discriminant is related to the central charge. So if we want a large C or large N limit, then this condition is a reasonable one to impose. And the second one is that we want the spectrum of polar states to be sparse. So these conditions that we impose on these holographic weak Jacobi forms tell us or are necessary to have compatibility with a semi-classical gravitational description. And in what I will do now, I will, for convenience, assume that these forms have weight 0, and I will just denote the weak Jacobi form by phi, okay? It turns out that in some of the examples, in one of the examples that I will discuss later on, I need to relax this assumption. And in the paper, you can find the relevant formulas, but the derivation of these formulas is very much, is very similar to the one that I'm going to present here for the case where the weight is 0.
Can I ask a question?
Yes.
So
Yes, please.
why are you restricting n equals 4? Is it, I mean, the elliptic genus of any CFT with Calabi-Yau target should be a weak Jacobi form.
Yeah,
So-
I'm not, this is just an example. I'm not restricting to just n equals 4. It's just to, it was just one example.
Okay.
Yeah. Okay.
Sorry. Well,
Right.
then in this
So-
case, it should be the unique weak Jacobi form of weight 0 and index 1. Or up to some rational constants, right?
Yeah, up to some constant, yeah.
Yeah.
Yes. Okay, so, right. So this condition, the first one here, it's, well, I already gave some motivation of why we impose it. Now I need to tell you what I mean by sparseness. So it turns out that the sparsity or the sparseness condition in weak Jacobi forms have been considered before by Nathan Benjamin and collaborators. And they found that if you impose the following condition on the polar or light states, so the same condition that HKS imposes, but translated to the context of weak Jacobi forms, then the asymptotic growth of states is going to be given by Cardy's formula, again, the version of Cardy's formula appropriate for weak Jacobi forms, that is valid in this regime where the discriminant scales linearly with this value delta naught. But it turns out that in our case, this version of sparseness is not sufficient. So we have to refine the concept of sparseness, and we're going to distinguish between two types of growths of the light states. So there will be fast growth. So fast growth is similar to the HKS condition, but it turns out that it can be generalized slightly by introducing this parameter gamma. Here gamma is some number greater than 0. And when the weak Jacobi form has fast growth, we will see that the behavior of the asymptotic density of states is going to be universal, okay? And it's going to be universal provided you are in this regime where delta scales again linearly with delta naught, but up to some number here, gamma, that is related to the gamma that appears here. But in addition, we will also consider forms that have slow growth. So by slow growth, we means that the growth is not quite this Hagedorn type growth, but it's sub-Hagedorn. So to be more precise, because there are two variables here, there's this n. So there's n, and there's delta n, delta L. Delta L is the value of L above the value of the ground state. And because there are these two variables, the way that we parameterize this slow growth is by requiring that f scales in this way when you scale these two variables. Okay, so, and this parameter alpha here must be less than 1. So an example of this, if you forget about this variable delta L, would be something like this. Something that is not Hagedorn, it's sub-Hagedorn, because in the exponential, you have this extra exponent alpha, which is less than 1. So in the case of fast growth, the behavior of the nonpolar states is universal in this regime, whereas for slow growth, it turns out that there's both universal or non-universal behaviors, depending on how delta is related to delta naught, okay? So there will be regimes where the low corrections are going to be universally determined just by basically by the ground state, and there will be regimes where the answer is not going to be universal. It will depend on the particular details of the spectrum, okay? And that will turn out to be important to reproduce the log corrections of the black holes that I mentioned before. Okay, so now let me describe how I'm going to extract these coefficients, these CNL coefficients for the heavy states. So for the states that I wouldn't,
Sorry, I didn't mean to interrupt. May I quickly ask, can you give me an example of a function which is a sparse, weak Jacobi form?
Yes, so the one of us, like the symmetric product orbifold of K3, for example.
Symmetric product orbifold of K3?
Okay. Well, a generic symmetric product orbifold is sparse. So so let me put it this way. Symmetric product orbifolds have two types of growth. One is like this, and the other one is like this one here, but with alpha equals 1/2. So I think, yeah, for symmetric product orbifolds, you have only these two types of growth possible.
But do you have an expression for the function that I can look at and convince myself that this is the growth?
You mean for the density or for the weak Jacobi form?
For the weak Jacobi form.
For this, well.
Because how do I check that for symmetric product that this is the growth if I don't have a function?
Well, so the one for the, say for the symmetric orbifold of K3, you just take the simplest one, this one, and then construct the symmetric product orbifold of this, right? You have like the DMVV formula. So once you construct the partition function, the elliptic genus for the symmetric orbifold of K3, the one for K3 is itself just this, then you can extract it from there. But this is something that has been studied in general by Alejandro Castro, Alex Bellin, and collaborators. So I don't think you need to have a specific example. Rather, you for the symmetric orbifolds, there is a seed and there's a formula. Like you can actually, using the DMVV formula, you can find a relationship between the parameters in the seed CFT, how those parameters, or the seed with Jacobi form, how those parameters relate to this growth here, to this alpha.
So when you say DMVV, do you mean the lift up the Siegel modular group, or are you still in the Jacobi form? This expansion of the Siegel modular form into Jacobi forms now?
Yeah, there is this DMVV formula that allows you to construct, I think it's the generating function of the...
Yeah. This is the generating function of Hilbert scheme of M points on the K3 surface. So you're saying that each individual piece in the generating function is going to be a sparse Jacobi form. Is that the claim now, or?
No. My claim was that they have. My claim was, well, what I was trying to say is that I don't have a specific example of. So for the case of symmetric orbifolds, one way that you can extract this is by trying to use this formula and properties of the seed to extract this the conditions for the resulting weak Jacobi form to be well, it will be sparse, but to be either fast growing or slow growing.
Okay, sorry, I apologize for cutting you off.
Yeah.
Maybe I have a few follow-up questions. I'll ask you a bit later.
Sure.
Sorry.
Yes, please.
Yeah, thank you.
Yeah, thank you. Okay, so yeah, now I would like to tell you how I extract. So my goal is to extract these CNL coefficients for heavy states, and which I would interpret as black hole microstates in the context of gravity. Once we put holography on top of this, and the way I'm going to do it is by promoting these coefficients to continuous distributions. So the CNL coefficients depend on these variables N and L, which are discrete, and I'm going to replace them by some function rho of N and L. Again, I will use the same notation for simplicity, where N and L are now continuous variables. So in this case, the Fourier expansion of the weak Jacobi form that I showed you before is given by an integral of this form. And I can use exploit the modular symmetry that I have, and then do an inverse Laplace transform to write the density of states in this way, where here this function P is what's called the crossing kernel. So this crossing kernel is defined in this way. Here you can already see in this term is a term that comes by doing this inverse Laplace transform, and this term here comes basically from the modular S transformation. I have not specified the contour integrate. I have not specified here exactly how you do the integration. You have to be careful about using the right contour. But if you are careful, you get an expression of this form, where here something worth mentioning is that this I here, it's a Bessel function, a modified Bessel function of the first kind, and its index is -3/2. And these -3/2 will be important soon. So what you can do with this Bessel function is you can consider the case where the argument is large. So in the case where the argument is large, these parameters here are large, you can expand the crossing kernel in this way with corrections that are exponentially suppressed. And you see that when you consider a polar state, so remember we have, we're interested in this formula here for the density of states. So there's an integral over n prime and l prime. So there's an integral over delta prime and l prime. So when delta prime here is less than 0, so when you have a polar state, this is a good old exponential. But when it's greater than 0, which would correspond to a non-polar state, it's oscillatory. So this is telling us that in the answer that we're interested in, which we're interested in extracting these coefficients in the log corrections when certain parameters are large, so that we can ignore other numbers. Only these terms, the exponential terms, will contribute. So what we can do is we can approximate the crossing kernel as follows. So we have the same expression.
Can I ask a question? Have you done already some approximation, or that expression in terms of Bessel function is exact?
This one is exact. This one is just doing this integral here.
So this formula, which relates rho as an integral of P and rho, so is it analog of Rademacher formula?
I will compare it soon. Okay. It would be sort of like the analog if you promote these discrete coefficients to be continuous, which I will discuss it soon. Thanks for the question. So because some of these terms are oscillatory, we have, or rather because this expression is dominated by the polar terms, we can do a further approximation of the crossing kernel. So we can split the density of states that appeared on the integrand into two parts, the polar and the heavy part, and we're going to ignore the non-polar or heavy part, so that our approximation for the density of states is going to be given by an expression that receives contributions only from the density of light states. So in that case, it is you see it's very important to understand how this density of light states grows as a function of the parameters. Okay, so there was a question about the Rademacher expansion, and what's natural to ask is how good is this approximation for the crossing kernel that we have made. So the Rademacher expansion is an exact formula for the CNL coefficients of the heavy states for weak Jacobi forms with this weight, k less or equal than a half. So I have written this formula in this way so that it's similar to the one I wrote before, where R here is the Rademacher, what I call now the Rademacher kernel. And there is some differences that I pointed out here, that in this case, we have a restricted sum over this variable L, and we're also summing only over the polar states of the weak Jacobi form. And the Rademacher kernel, when k equals to 0, which is what we are assuming for now, is given by an expression for this form. So there's a sum here over these different over this variable C. There's this term, these Klusterman sums, which for us, the relevant aspect of these sums is that they scale with the index in this way. So in the holographic setup where delta naught is much greater than 1, the index is related to delta naught in a particular way. So this term hidden in the Klusterman sum will be important, but there are also some phases that for us will not be important in this talk. But a crucial difference between the Rademacher kernel and the crossing kernel is that we have a different index for the Bessel function. So this Bessel function has a 3/2, whereas the one for the crossing kernel had a -3/2. And the difference in the index of the Bessel functions originates from different contours of integration in the definition of the kernels. But nevertheless, it turns out that when the argument is large, the argument of these Bessel functions is large, which is again the case we're interested in, the differences between the crossing and Rademacher kernels is suppressed and is exponentially suppressed. So this is just a fact about Bessel functions, which allows us to conclude that indeed the Rademacher and crossing kernels will agree up to non-perturbative corrections of this form. Okay, so in this sense, this crossing kernel that I wrote before is a good approximation in the problem we're interested in, where these parameters delta and delta naught are going to be large. Okay.
But you just said, answering my question, you said that crossing kernel provides an exact expression. So
well, this expression was this is just the integral of this expression. So sorry, this expression here is just, we've just performed this integral.
At which point you do an approximation?
Well, I think what we're not really allowed to do is to promote this variable to be a continuous one. So I think when we're I think the issue is this arrow here.
Okay, thanks.
Yeah. Okay, thanks for the question. Okay, so that's how I'm going to extract the asymptotic coefficients of these weak Jacobi forms. One in principle could have just used the Rademacher formula, but it's much simpler to do it using the crossing kernel. Okay, so now I'm going to extract these coefficients, and here's where the story becomes a bit complicated because there are many cases to consider, okay? So because I probably will not have time to discuss all of the black hole examples. I may be going too fast in this part, but if you have any questions, please stop me. So our goal is to estimate the density of heavy states when this parameter, the discriminant, we can think of this as the energy, is large. And the answer will depend on the density of light states and how these two variables are related to each other. So the first case that I will consider is the Cardy regime in the context of weak Jacobi forms, where delta, the discriminant of the state whose density we're trying to estimate, is much greater than that of the most polar state or the ground state. And in this case, it turns out that the integrand down here is dominated by the most polar term. Okay, so by the ground state in the weak Jacobi form, and this follows from the fact that the crossing kernel for any state other than the the crossing kernel of any state is suppressed exponentially with respect to the ground state. So in this case, the density of nonpolar states in this Cardy regime is given by this formula. So in this formula, we recognize two things. First, this term here is the Cardy growth, and these other terms are the log corrections. These log corrections are universal. They depend on the index of the weak Jacobi form. They also depend on the density of ground states, because the weak Jacobi form is not necessarily normalized to have a ground state equal to 1. It could have some other value, but that's all these log corrections will depend on. Okay, so in this sense, this formula is universal. It doesn't depend on the details on how the light states grow in this weak Jacobi form.
Sorry, can I ask? So
Yeah.
you're doing all this over SL2Z semi-direct Z2 is a Jacobi group, right?
Sorry, say that again.
The group, the Jacobi form, they're all SL2Z semi-direct Z2 Jacobi forms, like phi 0, 1, phi minus 2, 1.
Yeah.
So there,
Yes.
maybe this is where I think I'm slightly lost. But there, okay, if I have the space of weak Jacobi forms, I know that this is finitely generated by the ring phi minus 2, 1 and phi 0, 1 for SL2Z.
But these are weak Jacobi. Sorry, these are weak Jacobi forms with a very large index. This is much greater than 1.
Yeah. So I can generate the space of all weak Jacobi forms over SL2Z, semi-direct Z2, by arbitrarily multiplying phi 0, 1 and phi minus 2, 1, like ad infinitum. So I can, if you want to give me like an index 300, weight 0 Jacobi form, then I just have to solve, I just phi 0, 1 to the power 300 or something like this. So my question is there, so just so that I understand, how are sparse weak Jacobi forms formed from this ring? I mean, I'm finding it a bit difficult to understand where the sparseness condition comes from if I know the ring a priori. Because even if you do the symmetric orbifold, I mean, it's still weakness is the condition. I know the ring by hand. I know what the Hilbert schemes are, so I can do this very clearly. How do I put the sparseness condition here?
Yeah, I think, well, okay. What I would guess is that there will be, so excluding the symmetric, so I think, okay. What I guess happens is you have a whole space of weak Jacobi forms. Some of them will meet the holographic conditions. Some will not meet the holographic conditions. So I'm focusing on the ones that do meet these holographic conditions, that they're sparse in the sense that I defined before.
But if I take a power of a weak Jacobi form, let's say you fix your index is, so this is for n equals 4 models, or for which models are you doing them right now? Or is it arbitrary?
So far it's arbitrary.
So far it's arbitrary. Okay. Okay, so let me formulate the question in my head. Sorry for interrupting you.
No problem. So this is what happens in the Cardy regime. The formula is universal. The formula we obtained before in terms of the crossing kernel is dominated by the most polar state. So the next case where things get more interesting is what I call the universal regime. So this is a regime where delta satisfies this condition, which basically means that it's linear in delta naught. So this ratio is going to be held fixed as delta and delta naught are made larger and larger. So in this case, it turns out the answer is not dominated by the ground state. It's dominated by states that are still close to the ground state. So they're very light. And we can approximate this density of states by an expression of this form. So these terms here come from the crossing kernel. And this phi L here, it's a density for the light states, literally, and it takes this form. And here tau and z are these potential state values of order 1 in the regime where these ratios are fixed. And so you see that the answer explicitly depends on the density of light states. So again, because this phi L is sensitive to the growth of rho L of the light states, we need to be careful about whether the form grows fast, meaning this Hagedorn type growth, or it grows slowly, which is a sub-Hagedorn type growth of this form, okay? However, it turns out that in both cases, as long as these parameters up here are large, this density of this contribution from the light states is just given by the ground state degeneracy. Depending on whether you have a fast or a slow growing form, there will be some extra contributions, but these are contributions that are of order 1. So are not relevant for the question we're trying to answer, which are the log corrections when these parameters are large. What does change, depending on whether you have a fast or slow growing form, is the regime where the formula here is valid. So this is, again, a universal formula, is the same one we found in the Cardy regime. So when you have a fast growing form, this formula is valid in this regime. When you have a slow growing form, the result is valid instead in this regime. Okay, so this regime is, we called it a universal regime because the corrections are insensitive to the distribution of light states. They do not depend exactly on how the light states grow. It shows that sparse weak Jacobi forms can satisfy a weaker version of the HKS bound, which can be done when this value of gamma is greater than 1. But there's something more interesting that, well, I have not shown explicitly, and is the fact that this Cardy type of growth that we have here in blue, in the case of slow growth, turns out to hold in more general cases. So in an extended regime of validity, it holds when delta is scales linearly with delta naught, but it's greater than delta naught, but also when it's less than delta naught, okay? So there's an extended regime of validity where Cardy's formula, so the leading term in the asymptotic growth states works. So this motivates us to look at what we now call the non-universal regime. So the non-universal regime is described by this formula. So here, the discriminant delta is less than delta naught, which is the value for the most polar state. So in this case, it turns out that the integrand down here is no longer dominated by the very light states. So the previous approximations are not valid. And the way that we evaluate this density of states is by doing the saddle point approximation, okay? So this non-universal regime works only for slow forms, so slow growing forms. And you see that when we do the saddle point approximation, the exponential growth in the form is going to be competing with the Cardy term. This exponential term will also control the location of the saddle. And so it is convenient to have another parameterization of the density of light states of slow growing forms, which I have written here. So what I've done is I've explicitly written down the contribution of the ground states. I've written some polynomial growth that some polynomial growth that will affect the logarithmic corrections. And then I have still this exponential growth, which is characteristic of slow growing forms, okay? And with this parameterization of the density of light states, I can go ahead and use the saddle point approximation to try to extract the density of states here. But it turns out that even this is a bit complicated. So we end up considering different cases which will be realized in the examples that I will discuss later on. So because I'm running out of time, I'm going to basically skip some of the details here and just tell you the following. So we consider certain distributions that we call democratic, where the parameters scale in a democratic fashion. In this case, and assuming that alpha equals to 1, so this is the type of exponential growth of the weak Jacobi form, you find that the density of states becomes dependent on the details of the weak Jacobi form. So this factor here of omega is parameterizing the polynomial growth of the light states. The exponential growth of the light states also goes into this factor of 3/2. You don't see it explicitly because I've said alpha equals to 1/2, because I will use that later on. And you still have the Cardi growth that we had before. Okay, so again, because doing this, I'm trying to do this saddle point approximation for slow growing forms, and I'm considering 2 different cases that appear in the examples later on. There are these democratic distributions. There are also something that we call autocratic distributions, which are distributions where we only care about one of the parameters of the weak Jacobi form being large, for example, n, so that the density of light states effectively becomes neutral. It does not care about the other parameter. So in this case, we can be very explicit about our parameterization of the density of low states. So we assume that the density of low states scales in this way. There's a polynomial growth parameterized by omega, and then there's this exponential growth that is parameterized by this gamma and this alpha. Okay, and then we try to solve the saddle point equation, and we end up with an equation of this form that we cannot solve analytically. So we have to make another assumption, and the assumption is that we can solve it perturbatively, provided that the value of delta is related to delta naught in these 3 possible ways. So when delta and delta naught are related in this way, it's possible to solve this perturbatively. So we find 3 additional regimes that I will just skip, or maybe no, maybe, yeah, I think this is interesting. So I'll tell you what happens. So in this regime, the answer is given here. There's still a Cardi type of growth, and the log corrections depend on the details of the weak Jacobi form. Okay, that's what happens in this regime. The reason I'm stressing this is because there's this other regime where delta is much less than this value, where the leading growth of the asymptotic states is no longer Cardi. Okay, in some sense, the density of light states, so remember the density of light states goes like e to the 2 pi gamma n to some value alpha, wins versus the Cardi growth. So the log corrections still depend on the details of the weak Jacobi form, but the leading behavior, the leading exponential behavior, does not look like Cardi. So we don't expect this case to be relevant for black holes. So this case turns out not to be so interesting. But there's a marginal case that turns out to be interesting, which is the regime intermediate between the previous 2. So that's the case when delta scales exactly in this way. So this means that there's maybe some factor of order 1, but in the limit where delta naught is much greater than 1, delta must scale in this way. If this happens, then it turns out that the exponential growth in the density of light states, which is given here, is comparable to the one of Cardi. So the final answer looks something like this. There's still sensitivity to the data of the weak of the light states of the weak Jacobi form. But interestingly, the leading behavior scales like Cardi, but it's not quite Cardi. So there's this factor of zeta here, which is a number of order 1. So in the limit where delta naught is much greater than 1 and delta scales, as written up here, this zeta will be something that depends on alpha and on ratios of these variables. that is not universal, okay? It scales like Cardi, but it's not quite Cardi. So you may wonder if this has any application to black hole physics, where the classical formula for the area of the black hole is given by the Cardi formula. It turns out that it is relevant, but I don't think I have enough time to discuss it today. But in any case, it turns out that this case is relevant for black holes. Okay, so I've tried to summarize what I've said here, and this looks a bit complicated, but let me try to explain what's going on. So I've plotted the log of delta over delta naught here. HKS is basically this point here. So if you assume that your light states grow fast or slow, and you're in the regime in this line, then you find that your log corrections are universal. They depend only on the index and the degeneracy of ground states. However, if you're in this regime, you find that you can still find a Cardi type of growth for the leading exponential, but your log corrections will be non-universal, and the growth of your light states has to be slow. If it's not slow, our approximations break down, and you need to consider a lot of other terms that we have ignored. And if you're in the regime where this delta is less than this value, 2 alpha minus 1, then the formula for the leading behavior is not Cardi, and so it's not gravitationally relevant. So the regimes of this weak Jacobi form, or that are relevant in the gravitational context, are shown here in this plot. And this case here turns out to be well, it turns also, even though it's right on this line where you cannot quite get the Cardi formula with the right coefficient, it turns out to still be relevant in the entropy, in extracting the log corrections of certain black holes. Okay, so this was sort of like the first part of the talk, which I realized I've been too slow. So I will not have time to tell you all the details about how we extract the log corrections to the black hole entropy, but let me try to give you just a general picture of how we try to do this. And the general picture is that, well, the log corrections of black holes have been computed using the quantum entropy function that basically computes the Euclidean path integral in ADS2. So the idea here, which is the near horizon region of a BPS black hole. So the idea is that you go away from the near horizon region where you have, again, the full black hole, you uplift to some higher dimensional black hole, and then take again the near horizon region so that you land on ADS3. And in this ADS3, you can write down an index describing the degrees of freedom of supergravity in this background. So it will be ADS3 times something else. And from this weak Jacobi form, you can apply the formalism we described before to extract the log corrections. Okay, so the first case where you can apply this is to quarter BPS black holes in 4D, n equals 4 supergravity. So in this case, it turns out that the logarithmic corrections vanish exactly. And the goal is to show that this happens using the technology we developed before. And the crucial part in doing this, well, there are two parts. The first is to identify the correct index. So we know that the spectrum of supergravity on this background is organized into chiral primary representations of the n equals 4 superconformal algebra. And the elliptic genus of supergravity gives us a signed count of these states. And it corresponds to a weak Jacobi form of weight 0 and an index that scales with n, which is the number of copies of a symmetric orbifold. So this is the same elliptic genus as that of the symmetric orbifold of K3. And the crucial part to extract the logarithmic coefficients from this weak, the logarithmic corrections to the entropy of black holes from this weak Jacobi form is to find in which regime of the weak Jacobi form we are. And this can be done by using the dictionary relating the lower dimensional black hole to the higher dimensional black string that happens in this uplift that I mentioned before, but unfortunately I have no time to discuss. And when you do this, you find that the relevant regime to extract these logarithmic corrections is given down here and corresponds to the universal regime that we discussed before. Okay, and so if you go ahead and apply the formula that we found before to compute these logarithmic corrections, you find an answer of this form. And this is an answer that depends only on the ground state degeneracy of this weak Jacobi form, which is determined by this C naught. So C naught here is the ground state degeneracy in the elliptic genus of K3, which is known to be 2. And here I explain exactly where this 2 is coming from 2 different perspectives. But the moral of the story is that using this approach, you indeed find that the logarithmic corrections in that case vanish. Okay, so it matches the computation of the log corrections in ADS2 using this quantum entropy function. So that's one case where this works nicely, but this is also a case that is very well understood, both from the ADS2 point of view, also from string theory. So there are 2 other cases that I wanted to consider. One is the log corrections to the entropy of BMPB black holes. So in this case, the log corrections are given by this number. There's a factor of -4. And we can do the same approach. So we start from the near horizon region of this black hole, and then we uplift. So now we have the near horizon region of some black string. And we have the same elliptic genus describing the theory in this background. But what has changed with respect to the previous example, where we were, sorry, this one here should be 5D. What differs from the example in 4 dimensions is that the relationship between the parameters of the weak Jacobi form and the black hole have changed. So when the charges of the black hole are large, which is where the calculation of the log corrections is reliable, the variables of the weak Jacobi form are related in a different way from the previous case. So in this case, the formula looks something like this. There's a typo here. This should be delta, sorry, no, this is okay. This is not delta. This is delta naught. So this delta is less than delta naught, but scales like delta naught to the power 1/2. And in this case, it turns out we are in the non-universal regime. So if you're in the non-universal regime, you have to be careful about the growth of your weak Jacobi form. And it's only the case where the form grows slowly that we can extract the logarithmic corrections. And it turns out that this is indeed the case. So the form grows in this way, where these functions satisfy these conditions when you make the parameters large. And these are numbers that you can extract from the weak Jacobi form. So alpha, what determines the exponential growth of the light states, is 1/2. And omega, which determines the polynomial growth of the light states, is given by this value. Here again is C0 and C1 are the degeneracies in the elliptic genus of the seed of K3. So this one is 2, and this one I think is 20, and this is what gives you this value of -17/2. So then you use the formula we found before for all these different regimes. You plug in these numbers, and you see that indeed this density of states of the weak Jacobi form with this in this non-universal regime indeed matches we can indeed extract the coefficient of the logarithmic corrections of the lower dimensional black hole. Okay. How much time do I have?
Well, your time is sort of up, but you can use 3 more minutes or so.
Okay, thank you. Yeah, so let me describe the last case, because I think the last case is actually the most interesting one, because it's the most subtle one. And so this is the case where we try to reproduce the logarithmic corrections of half BPS black holes in 4-dimensional n equals 2 supergravity. So in this case, the logarithmic corrections are a bit more complicated. So they depend on the number of vector and hypermultiplets, and these are numbers that characterize the Calabi-Yau threefold on which you compactify to get this 4-dimensional theory. So you can think of this theory, you can obtain, one of the ways you can obtain this series from a compactification in theory on a Calabi-Yau threefold times a circle, okay? So the goal is to reproduce these logarithmic corrections with the technology that we have developed. And we proceed as in the previous two cases. You uplift the ADS2 geometry to ADS3. So in this case, the full geometry is ADS3 cross S2 times the Calabi-Yau threefold, which is the near horizon region of a 5D BPS black string considered in this paper, the MSW string. And in this case, the situation is way more complicated than in previous cases, because it turns out that the elliptic genus vanishes, so that's not something we can consider. We have to consider a modified elliptic genus, and there are several subtleties. But the bottom line is that when you use the relationship between the parameters that appear in your weak Jacobi form versus the parameters that characterize the black hole, you find the following relationship for the discriminant of the black hole states, or of the black hole microstates, which is given down here. Which is given down here, which tells you that we are again in the non-universal regime. And if you are in the non-universal regime, your weak Jacobi form better grows slowly, which indeed it does. But you have to extract the growth of this weak Jacobi form. And the way that we do it, well, people have computed the spectrum, the contributions of supergravity to this modified elliptic genus, and the formula is given here. There are again some subtleties that I don't have time to explain, but the important point is that the Calabi-Yau data appears here. So it depends on the Hodge numbers of the Calabi-Yau, which can be related to the number of vector and hypermultiplets. And if you try to see how these contributions of supergravity grow, you find the following density of states, which is precisely what you expect for a slow growing form, where alpha is now 2/3, which is again less than 1, as it should be. And this value of chi determines the polynomial growth of the weak Jacobi form. Now, why is this case the more interesting one? I think is because, well, besides the subtleties in trying to get this result, when alpha equals 2/3, the relationship between delta and delta naught is this one, which is the marginal case where a gravitational interpretation of the weak Jacobi form is still may still be possible, because what happens is the density of states, which you see down here, well, it looks very complicated, but the exponential growth is not quite Cardy. So there's this theta here that is telling you that it's the entropy would be given by the area of the black hole, as written down here, times some number that is not 1, as you would expect it to be. But interestingly, after you take into account all of the complications of this example, you find that the log corrections exactly match what has been computed before in the context of ADS2. Okay, and this matching is sensitive to the weight of the weak Jacobi form. So this is an example where the weak Jacobi form has a weight. It depends on the ground state degeneracy and a proper accounting of the light spectrum, which, as I mentioned, there are some subtleties, but I don't have time to discuss. So the reason why this is particularly interesting is because if you try to interpret this result from the point of view of the gravitational path integral, you find that quantum effects are taking over the classical result. So the classical result would be just having the area of the black hole over 4G. But you see that when you consider the quantum corrections, then the classical result is modified by this data, at least in this approach. Okay, but the log corrections do indeed match. So just to conclude, actually I don't have conclusions. I just have this plot again, which I hope is not too confusing. And what I will put in this plot is the different examples where this formalism, where we apply this formalism. So one example is sort of here. This is the 4-dimensional black holes. Then there's another example for the 5-dimensional ones, which is somewhere here. And then there's the last example, which was this n equals 2 black holes in 4 dimensions, which is sort of the marginal example that lies here. Okay, I think I've taken too much time, so let me conclude here.
Okay. Thanks very much, Luis, for this very interesting talk.